So today we're going to start Chapter 6, Section 1 of our normal textbook. We're back to our normal textbook, and we're basically going to introduce you to the idea of a new unit of measure for an angle. The new unit of measure we're going to be talking about is called a radian, okay? And the best way to describe a radian is, right now what happens is, let's just, we have this coordinate plane. Let's pretend let's insert like a circle, and let's create an angle here, okay, which you've been doing, right? You have an angle. We call that angle theta. And you know that if you draw these lines from the center to the circle, these form what's called a radius. And when you have these two radius, you all of a sudden get this intercepted arc here between it, right? It kind of breaks the whole circle into that arc. And up until now, we've measured degrees, or we've measured angles in terms of degrees. How many degree units from the initial side is the terminal side. Now we're going to talk about radians. You may say, well, I've never heard of radians. Well, it's true. Radians are very popular in calculus and higher level math like physics and things like that. And radians kind of make sense because when we talk about angle measures are always relative. Like if I say turn 90 degrees, well, my 90 degrees from where I'm standing is going to be different from your 90 degrees where you're standing. And so it's a very relative term from one perspective, whereas a radian is pretty much a length. So for example, let's say that this angle is, 30 degrees in angles, in degrees. In radian, we're going to measure it by the length of this arc here. What is the length of that arc? And so that's not relative anymore. That is a set value. So you're said to have 1 radian when theta, let's say, would be 1 radian, okay, when the arc here, the intercepted arc, is equal to the radius, okay? So your radian is equal to the arc length over the radius, okay? So think about it, it's a length over a length. And so when the arc length happens to be the same as the radius, as a radius, then your theta is 1 radian, okay? Because r over r is 1. So 1 radian that's the unit of measure we use. And so let's try to talk about, what do you think a radian equals in terms of degree? Like, how is it even compared, right? Well, let's think of this in terms of a full revolution. Let's say that our angle, instead of being like a 30 or a 45 or a 60 degree angle that I kind of did there, let's create an angle that is 360 degrees, right? That's like in black. I just kind of wanted you to see it. So if I have an angle that is 360 degrees, I know that that's 1 complete revolution, right? 1 complete revolution. I don't know why I wrote that. Revolution, okay? Well, in terms of length, right, in terms of radians, what is the measure of 1 complete revolution in terms of the circle? Well, you know that the entire circle, if you were to measure the length of the entire circle, that's equal to the circumference, right? So the circumference of the circle, we know, is 2 times pi times the radius, right? So if I wanted to do in radians, if I wanted to figure out what a full circle is in terms of radians, I would do, again, the arc length. Well, the arc length would be the entire circumference of the circle, which is 2 pi r, over the radius. And notice my r's would cancel, and I would be left with 2 pi radians. If I want to do short, I do rad, okay? So 2 pi radians. So 1 complete revolution is 2 pi radians, okay? So now now that we know that, let's think about that. In terms of degrees, this is, let's say, 0, this is 90, this is 180 degrees, right? This is 270 degrees, and this would go back to 360. And that's obviously if I'm going in a positive counterclockwise direction, okay? Now let's do the same thing in terms of radians then. Well, I know 0 radians is 0 degree and 0 radians are going to be the same. And I already just showed you that an entire revolution in terms of radians is 2 pi radians. Well, let's think about what the other values might be then. What might 180 degrees be? Well, I know 180 degrees is half of a full rotation, half of 360, right? That's how I get that. So I know that in terms of radians, 180 degrees would be half of 2 pi. Well, half of 2 pi is pi. And so 180 degrees in terms of radians is known as pi radians. If I was to say 90 degrees, well, I know that 90 degrees, right, is a quarter of the 360. It's a quarter of the circle, so it's 90 degrees. Well, in terms of radians, then, it would be a quarter of 2 pi, which would be 2 pi over 4 or pi over 2. So 90 degrees is equivalent to pi over 2 radians. And lastly, I'll try the 270. If I do 270 degrees, I know that I get that from doing 3/4 of 360 degrees. That's how I get 270. So if I want 270 degrees in radians, it's 3/4 of 1 complete revolution, which is 2 pi. So it's 6 pi over 4 or 3 pi over 2. So again, this is in radians. So it's kind of interesting, how we label this and how we sort of visualize it. But let's kind of clarify. So here we have 180 degrees, and we know that that's pi radians. So there are some important numbers, that you definitely want to have. You want to know, again, that 360 is equivalent to 2 pi radians, okay? You want to know that 180 is equivalent to pi radians, basically half of 2 pi. And if I want to know exactly what a radian is, let's use that equation. We say 360 degrees equals 2 pi radians. If I want to know how many degrees is one specific radian, I'll divide both sides by 2 pi. Okay? And if I do 360 divided by 2 pi, I'm going to get approximately 57.3 equals 1 radian. So 57.3 degree equals 1 radian. So a lot of times what we do is we approximate even more, and we basically say 1 radian is about 60 degrees. So if I think about it in terms of, a single number, not like pi radians and things like that, if I think about it in terms of 1 radian, then I know that in my coordinate plane, if it's about 60, 1 radian would be about here, right? Another 60 degrees this way would be my second radian. Another 60 degrees this way would be my third radian, right? 60 degrees this way would be my fourth radian, right? This way would be my fifth radian. And back at 360, I'd be at 6 radians. And so what happens is 1 complete revolution is approximately 6 radians. And that makes sense, right? Because again, 2 pi is 1 revolution. And if I just multiply 2 times pi, which is 3.12, I get 6.28 radians. Okay? So I get 6.28, and again, we just approximate it to 6 radians. So this is considered like inexact. This is an approximation, okay? If I do pi is exact, okay? So it's more exact to say 1 revolution is 2 pi than to say 2 pi radians, than to say that 1 revolution is 6.14 or 28 radians or 6 radians. So most of the time what we do is we talk in terms of pi because it's more exact. But you want to start understanding your quadrants, and you want to understand that if you're given, 1.2 radians, it's probably going to be in quadrant 1. If you're given 2 radians, it's probably going to be in quadrant 2. Or it's definitely going to be in quadrant 2. If you're given, something between 3 and 4 radians, it's going to be in here. And it's really important that you understand where the radians fall. Just like you do with degrees. You want to know, where does 60 degrees fall? Quadrant 1. Where does 120 fall? Quadrant 2. So understanding the quadrants and the relationships with radians is super important. Okay. So I think we've covered all the important things for this slide. Again, there's a formula here that I want to, touch upon. Again, an angle in terms of radian is the arc length over the radius. And if I just kind of play around with the equation, if I multiply both sides by r, times r, I get that S equals, right, theta times r. So I can kind of manipulate the equation a little bit, okay? Again, S represents the arc length, okay? And R represents the radius, okay? And theta, again, is the angle in terms of radians. So now, if I want to find coterminal angles, again, I know that one complete revolution is 2 pi. So that means if I want a coterminal angle, if I was given a degree, if I gave you 120 degrees and I asked you for a coterminal angle, you would say, okay, no problem. I'm going to do 120 plus 360, and I'm going to get 480 degrees. That's coterminal. Or I could do 120 minus 360, and I'll get negative 240 degrees. That's coterminal. And that would be the same thing you would do with an angle in pi. Let's say that I give you an angle, let's say angle pi in radians, pi radians, and I want a coterminal angle to that. We know pi is 180, right? If I want a coterminal angle, I'm going to take pi and I'm going to add 2 pi to it. So I know that 3 pi radians is coterminal with pi radians, okay? If I subtract 2 pi from it, I'm going to get negative pi. Well, negative pi radians is going to be coterminal with pi radians. And again, let's visualize that so you can see it. I know that pi radians is 180 degrees, so it's actually this angle. And the terminal side, I'm going to put it here in blue. Well, now 3 pi radians, again, I'd say, okay, well, 2 pi is 1 rotation, and pi is a half rotation. And guess what? I'm on that blue side. It's coterminal. Negative pi, I start here and I go negative this way, and it's also coterminal. Notice all of those angles end at the same terminal side. So again, in radians, I just add or subtract 2 pi. Now, sometimes it's not as easy as you think because you get a lot of fractions when it comes with radians. Let's see the next slide. So here I have a slide and it's asking me find a coterminal angle to 17 pi over 6. Well, I know coterminal angle, I'm either going to take 17 pi over 6 and I'm going to add 2 pi to it to get my answer, or I'm going to do 17 pi over 6 and I'm going to subtract 2 pi and I'm going to get another coterminal angle. We always like our coterminal angles best to be within 1 revolution. So that's between pi and 2 pi. And right now it's kind of a bigger, this is more than 1 revolution. But let's just do the math and I'll show you which one we would prefer. If I wanted to convert 2 pi to a fraction over 6, because again, to add or subtract, my denominators have to match. So I know that I have to multiply the bottom by 6, so I'm going to have to multiply the top by 6. And I know that 12 pi over 6 is equivalent to 2 pi. So I'll do 17 pi over 6 plus 12 pi over 6. And that's going to be 29 pi over 6. So 29 pi over 6 is coterminal with 17 pi over 6. If I do the subtraction, 17 pi over 6 minus 12 pi over 6 equals 5 pi over 6. So this is also coterminal. And if I subtract another 2 pi, I'm going to get another coterminal angle. In fact, I'll get a negative one. Now, which one is preferred? This one. Because this one is within 1 revolution. Remember that here's 0, here's pi over 2, here's pi, here's 3 pi over 2, and here's 2 pi. That's 1 full revolution. Well, 5 pi over 6 is in this quadrant. I'm going to go and I'm going to stop at about here. Okay, and so that is really where I prefer to have it rather than 29 pi over 6, which is multiple revolutions. Okay. But again, they're all coterminal. They all end in the same spot. So I go now to the second problem. I have negative 4 pi over 3. So again, if I'm finding a coterminal angle, I'm going to add 2 pi. And I could subtract as well, okay? So if I'm adding, I need a fraction that has a denominator of 3. So again, 2 pi over 1. If I want to make the denominator 3, I have to multiply by 3. So I do the same thing to the numerator. So I know that this is negative 4 pi over 3 plus 6 pi over 3. And that's going to give me positive 2 pi over 3. So 2 pi over 3 is one coterminal angle. If I had subtracted the 2 pi, so I'll subtract the 6 pi over 3, I get minus 10 pi over 3. And again, that's also coterminal. Now for me, I prefer this one. This is within one revolution and it's positive, which is what we want. So that's what I would go with. Now, a lot of times you're going to want to compare. You're going to want to go from degrees to radians or radians to degrees. You're going to need to know how to do that, okay? Sometimes you're going to need to do it because you're going to be asked something in terms of, you're going to be given degree and the answer has to be in radians, so you have no choice. And other times you're going to want to convert just to kind of visualize sometimes where an angle is if you get confused. So you want to know how to do it. So what happens is, we know that 180 degrees equals pi radians. And so what you have to do is you know that they are equal in value. So if I multiply something by pi over 180, okay, because I know that this is equal, pi radians, this is really pi radians over 180 degree, I know that this is going to be equivalent. So what I'm doing is, that's going to be my conversion factor, okay? And what I want to get rid of, the unit of measure I want to get rid of is going to be in my denominator. So if I'm given degrees and I want to go 2 radians, I'm going to put degrees in the denominator spot. So for example, let's say that I have 30 degrees and I want to go to radians. I'm going to multiply 30 by pi radians over 180 degrees. And what's going to happen is, and instead of doing degrees, let me write the symbol. What happens is the symbols are going to cancel because one's in the numerator, one's in the denominator. The 30 and the 180 can be simplified to 1 and 6. And so when I multiply across the top, I'm going to get pi over 6. So pi over 6 radians is equivalent to 30 degrees. And if I want to go from radians to degrees, I'm going to use 180 in pi, but I'm going to use 180 in the numerator spot. Because again, if let's say I have, let's do this backwards. Let's say I have pi over 6 radians, right? Let's do radians. And I want to go to degrees, I'm going to do 180 degrees up top, and I'm going to do pi radians at the bottom. These will cancel, leaving me with 1. The radians cancel, and then I'm left with, let me do 1, this is 30, and when I multiply across the top and the bottom, I get 30 over 1, or 30 degrees. And so whatever I'm given, I'm going to look at it, I'm going to see what I've been given, and then I'm going to multiply with that degree or that radian I've been given in the denominator spot. So let's kind of work here. So I look at number 1 and notice I've been given degrees. And what you want to do for degrees, you want to look for the degree symbol, okay? If it's not there, okay, it's a radian. So if you notice number 10, this is 5. You might think that that's 5 degrees, but that's not true. That's 5 radians. And as we talked about, you saw that 5 radians was in the 4th quadrant. This is 2 radians, which you saw when we talked about it. This is in the 2nd quadrant. 2 radians is about 120 degrees. 5 radians is about 300 degrees. Remember we talked about 1 radian is about 60 degrees. So unless you see the degree symbol, it's a radian. So because this is degree and I want to get rid of degree, I'm going to multiply it by 180 degrees and pi is going to be at the top. I like to simplify before I multiply, and I know that 45 goes into 135 3 times, and 45 goes into 180 4 times. And so now I can multiply across the top, and I get 3 pi over 4. So my answer is 3 pi over 4 radians. Number 4, again, I see that this is a degree. So I'm going to multiply by pi over 180. And again, I like to simplify first. 180 goes into itself once. 180 goes into 540 3 times. Okay, so I get 3 times pi over 1, or 3 pi radians. That's my answer. Okay. I get the next one, it's 45 degrees. So I know I'm going to multiply by pi over 180 degrees. Okay. And I know that 45 goes into itself once, and it goes into 180 4 times. And so my answer is going to be 1 pi over 4 radians. And we don't always write the word RAD. We just know it's radians, but I'm just doing it to do everything the right way for you. So we have 90 degree over 1. We're going to multiply that by pi over 180. And I know that 90 goes into 90 once. It goes into 180 twice. And I know that my answer is going to be pi over 2 radians. So all of these were in degrees, and I converted to radians. Now I notice this one, it doesn't say radians, but again, when you see the answer in terms of pi, you know that it's in radians, okay? And so again, if they gave it to me in radians, I know that I'm going to want to convert it to degree. So what I'm going to do is I'm going to put the degree, which is what I want, up top, and I'm going to put the radians at the bottom. And now I simplify. So I know pi and pi cancel out. 6 and 180, I can simplify that, and I'm going to get 5 times 30 is 150 degrees. And there's my answer. When I go to the second one, again, I see the pi, so I know this is in radians. I'm going to put degree up top, pi at the bottom, cancel the pi, 4 and 45 here, and 3 times 45 is 135 degrees. Okay, and again, notice, right, here's 3 pi over 4 is 135 degrees, and here we got 3 pi over 4 is 135 degrees. We sort of just work backwards. You can have negatives. That's not a problem. Again, this is still in radian form, so I'm still going to multiply by pi in the bottom and 180 degrees at the top. I'm going to cancel that. 2, and this becomes 90. And I'm going to get negative 90 degrees. And that's okay. You can have a negative degree. Now here I know this looks a little weird because, again, this is in radians, but the process is still the same. It's 5 radians over 1, let's say, or 5 over 1 radians times. And again, I want to get rid of radians, so I have a pi there and 180 degrees here. So I know that my numerator, right, my radians are going to cancel. This is like radians, right? And again, you don't really have to write radians. I just know it is. Let me just kind of fix it. So 5 over 1 times pi in the bottom, 180 degrees at the top. 5 times 180 degrees. 180 times 5 is 900. So 900 over pi. And now what I'm going to do is just divide 900 by pi. So 900 divided by pi is going to give me 286.5 degrees. And that's my answer. So again, here with 2, I know this is radians because I don't see the degree symbol. So I'm going to do this. I'm going to convert it to degrees. I'm going to get 360 degrees over pi, and I'm going to divide. So I'm going to do 360 divided by pi, and I'm going to get 114.6 degrees. And there you have your answers. This is your conversion, and this is the process of going from one form to the other. And it is super important, guys, that you learn how to do this. Lastly, we're going to talk about arc length and area. And this was really an old geometry term. In the past, because you didn't know how to work with back in the day in geometry, you did not know how to do radians. So you would be given a circle. You were given a central angle. At some point, you drew something. They told you it was, let's say, 30 degrees. R was whatever it was, right? And if we asked you for the arc length, you had to use a ratio. We actually didn't even call it S. We called the arc length, let's say, X. And we said, well, to solve this, to find that length, you're going to have to do 30 over 360, because 360 is the whole circle, equals the arc length over the entire circumference of the circle. And if I at some point wanted to find the area of the circle, right? If I wanted to find the area of that, not the circle, but the sector, you did kind of the same ratio. You could extend it and say, well, the sector area, I don't know if any of you guys remember doing this, over the area of the circle, which is pi r squared. And so you'd set up these ratios and use proportional math to solve it. It was a little bit of a lengthy process, but that was because it was based on degrees. Well, now we have a shortcut. Now that you've learned radians, now we can apply radians to sector lengths and sector areas, okay? The important part, let me just kind of redraw this, okay? Now you're going to have a circle again. You're going to have a central angle, but that central angle is going to be in radians, okay? So the theta in this one, it has to be in radians for this to work, okay? The letter S represents the length of the arc, okay? And the R represents the radius of the circle. And if you have that combination, we have the formulas to solve these. So if I want to know the length of this arc, instead of having to create those weird proportions, all I have to do is know the formula S equals theta times R. Remember, theta is S divided by R. So if I'm trying to solve for S, if I just multiply both sides by R, I'm going to get S is theta times R. And again, theta has to be in radians, guys. I can't stress this enough. It's here. It tells you, okay? So that's the formula for arc length. And if I want the area of the sector, if I want to know what is the area of this sector in this circle, the formula is half times the radius squared times theta. So using these, we can solve a bunch of problems. So let's go to the next slide. So here they tell me a circle has a radius of 18.2 centimeters. It wants the arc length. They're looking for S, and it wants the area of the sector as well, okay? And they tell me that theta equals 3 pi over 8. So theta is in radians, so that's good. And my radius is here, so I have everything I need. The formula for the formula that I need for the arc length is S equals theta times the radius. So theta is 3 pi over 8, and the radius is 18.2 centimeters. I do it over 1, so I kind of can think of numerator and denominator. My numerator is now 3 times pi times 18.2, and my denominator is 8 times 1, or 8. So all you have to do is go to your calculator, guys. 3 times pi times 18.2 is like 171, whatever. I'm going to just leave it in my calculator, divide by 8, and I'm going to get approximately 21.4, and the unit of measure is centimeters. And that's my answer. That's my arc length. Now, the area, again, I'm going to use the formula. I know that the area is, again, half times the radius squared times theta, 3 pi over 8. So, again, what I like to do is I sort of like to write this all as numerators and denominators, if that makes sense. So 18.2 over 1 squared times, and then it's 3 pi over 8. Ultimately, I know I'm multiplying all my numerators together, and I'm multiplying all my denominators together, right? So I kind of come to my calculator, and I know order of operations. I know I have to square 18.2 first. So 18.2 times itself, then is 331 something, times 1, just itself, times 3, times pi. And I'm going to get some crazy numerator like 3,100, 3,000 something. And then I know I have to divide that numerator by 16. And so I kind of leave it in my calculator, and then I just get my final answer is 195.1 centimeters squared. And there's my area. So as long as you do your order of operations and you memorize these formulas, you're good to go. one last problem here on this slide. We're going to start, the circle has a radius of 18.2, just like before. Theta is 144 degrees, and they want the arc length, S, and they want the area of the sector, okay? So I'm almost ready to start, except for the fact that I have to notice that this is in degrees. And for this formula to work, it has to be in radians. So I have to start by converting. So I'm going to start, I know that 144 degrees, if I want to get rid of the degree, I have to multiply it. My denominator has to be degree, and my numerator is the pi, radians. So I get 144 pi over 180. That's going to be my answer, my theta in radians. Now, I can simplify that. I know 36 goes into both of these, okay? So 36 goes into 144 4 times, and 36 goes into 180 5 times. And so that is the simplified version, okay? So 4 pi over 5, okay? So my theta is 4 pi over 5, and now I'm ready to do my formulas. So again, I come over here. My arc length is going to be theta, 4 pi over 5, times the radius, which is 18.2 over 1. So again, I know my numerator is 4 times pi times 18. So 4 times, sorry, my calculator, 4 times pi times 18.2. It's like 228, and I'm going to divide it by 5. And I get 45.7. So approximately 45.7 centimeters. And then the area is going to be the area formula. So again, the area formula is 1 over 2 times the radius squared times theta. Okay, so again, and I have to do the math. So again, I'm going to come over to here, and I'm going to do 18.2 squared first times 4 times pi equals something like 4,000 something, and I'm going to divide that by 10, which is the denominator. And I'm going to get approximately 416.2 centimeters squared. So approximately 416.2 centimeters squared. It doesn't tell me what to round to, guys, so I try to use what they rounded to. Since they rounded to tenths, that's what I'm rounding to. And that's it, guys. That's the whole video. You have some things to memorize, some things to practice. Let me know if you have any questions.